All right, welcome everyone. Today we're unpacking a dynamic that is just incredibly fascinating and honestly super misunderstood. We're talking about the relationship between our bodies and the microbial world. In this explainer, we're going to dive right into the foundations of immunology to figure out what actually happens when we encounter a pathogen. We usually tend to think of our relationship with microbes as this constant, never-ending war, where any contact is just bad news, right? But the reality? It's way more complex, a lot more nuanced, and just beautifully elegant.
So let's kick things off by asking a really fundamental question right at the top. If a microbe enters our body, do we always get sick? Now, for a long time, the common assumption was just a big resounding yes. We're totally conditioned to think of germs purely as these tiny invaders that automatically trigger sickness. Well, we're going to shatter that preconceived notion right now. The answer is actually no. Merely coming into contact with a microbe and actually coming down with an illness, those are two completely different things.
Which brings us to Section 1. Encounter is not disease.
Literally from the moment we're born, we're constantly interacting with this massive invisible ecosystem. We've got countless bacteria and fungi just naturally hanging out on our skin, our mucosal membranes, not to mention the absolute microbial universe thriving inside our gut. Every breath you take, every bite of food you eat, every doorknob you touch, you're introducing new microbes to your body. And yet, we aren't constantly sick. Why? Because there's a really critical line drawn between two ideas here: colonization and infection. Colonization is simply when microbes, kind of like the staph bacteria that are naturally chilling on your skin right now, settle on our surfaces and just hang out. They multiply, sure, but without causing any obvious disease or tissue damage. They're basically just occupying space. Now, infection, on the other hand, means the microbe has successfully set up shop inside the host and kicked off a true biological interaction. But here's the wild part. Even an actual infection can pass by completely unnoticed without a single symptom.
Moving on to Section 2. Infection is an interaction.
Historically, we have a super simple, kind of one-way street view of disease, right? Find the pathogen, find the problem. Tuberculosis is caused by the TB bug, the flu is caused by the flu virus. And sure, identifying specific microbes as the bad guys was a massive triumph for modern medicine. But it left a really glaring question unanswered. Why do two people exposed to the exact same microbe have totally different reactions? Why does one person feel absolutely nothing, while the other ends up in the ICU? Well, this equation right here brilliantly illustrates the answer. Disease equals microbial factors multiplied by host factors. This is a massive aha moment in biology. It tells us that an infection isn't a solo act performed by a germ. It's a duet. The final outcome happens right at the intersection of the pathogen's traits, like how virulent it is or how many of them invaded, and your specific state. Your age, your genetics, how strong your biological barriers are, your current immune status, they all play a huge role. You really just can't understand disease by only looking at the bug. You've got to look at the host too.
That leads us right into Section 3, the biological journey.
So how does this whole interaction actually play out in real time? Well, this biological journey is more like a branching path with a bunch of variables. It is absolutely not a one-way street to getting sick. Step 1 is microbial exposure. But almost instantly your body throws up barriers. If a microbe can't get past your skin or your mucus, it just gets cleared out right then and there. No infection even gets a chance to start. If it does settle in, it might just lead to that colonization we talked about. But if it truly establishes an infection, we hit the third phase, the clinical outcome. And this is where things get super fascinating.
The real kicker here is that a successful immune response doesn't always look the way we assume it does. Once an infection actually happens, the outcome splinters into a few different possibilities. Sure, one option is total clearance, where your body completely wipes out the bug. But another totally viable, successful outcome is an asymptomatic or subclinical infection. That's where your immune system swoops in and controls things before you ever even feel a sniffle. Then, of course, there's clinical infectious disease, where actual tissue damage happens and you get symptoms. And finally, you've got persistence or latent infection. Think about the chickenpox virus. That thing can lie totally dormant in your nerves for literally decades, just kept in check by your immune system. In those cases, immune success doesn't mean totally eradicating the virus. It just means keeping that microbe locked down at a level where it can't make you sick.
Let's look at Section 4, two phases of immunity.
Up to this point, we've kind of talked about the immune system as our trusty, steadfast protector. But here's the twist. Our own biological defenses can actually act as a serious, double-edged sword. You see, in any infectious disease, tissue damage actually comes from two totally distinct sources. First, you have microbe-mediated damage. This is the one you usually think of, where the pathogen is in there directly wrecking cells or pumping out toxic substances. But on the flip side, we have immune-mediated damage. Think about the intense cytokine storms we saw in severe COVID-19 cases or a really bad flu. If your body's inflammatory response is way too aggressive, or if it just lasts too long, our own weapons will literally destroy the healthy tissues around the infection. Scientists Casadevall and Pirovsky actually framed this as the damage response framework. Basically, it means that falling ill isn't just about the bug being toxic. It's very often the result of the collateral damage caused by our own immune response fighting a war inside us.
And that leads us perfectly to the concept of appropriate immunity. You can think of this as the biological Goldilocks principle. The absolute best immune response is not the strongest possible response. No way! A hyperactive response is going to cause massive tissue damage, just like a super weak response would let the microbe run wild. Appropriate immunity is an immune response that is, well, just right. It's strong enough to effectively lock down the pathogen, but finely tuned and regulated enough to preserve and protect your own tissues. Next up is Section 5, Context-Specific Immunity. To strike that incredibly delicate balance we just talked about, the immune system has to act like a highly sophisticated biological intelligence agency. It needs to ask two really vital questions. What were we infected by, and where exactly is it? Because, honestly, a generic intruder alert is completely useless. Think about it. A bacterium multiplying outside your cells requires a completely different defense strategy than a tiny virus hiding directly inside your cells. Fungi and parasites, they have totally different sizes and life cycles. So your immune system needs highly specific intel if it's going to deploy the right weapons.
So here's how that biological intelligence network actually gets the job done. When a pathogen first breaks in, your innate immunity kicks on. Now, a lot of times we just think of innate immunity as this generic, immediate physical defense, just a way to buy some time. But it is so much more than that. It is actively gathering early intel on the pathogen's exact traits, its location, and what's happening to the tissue. It then takes this supercritical information and uses it to direct the secondary, highly specific adaptive immunity. It's literally telling the adaptive system, hey, we've got extracellular bacteria over here, send in the antibodies. Or whoa, we've got an intracellular virus, deploy the T cells. Remember, the best immune response isn't just the biggest one. It's the one that is perfectly tailored to the specific type and location of the infection.
Which brings us to Section 6, the delicate host microbe balance.
All right, so we've been zoomed in pretty close on the cellular level, but if we zoom out to the grand scale of evolutionary time, we see that this is absolutely not a static process. Pathogens aren't just sitting there waiting for us to destroy them, they are desperately trying to survive and multiply, just like any living thing. So what we really have here is a dynamic evolutionary arms race. Step 1, the host detects the threat and mounts a defense. Step 2, the pathogen mutates. It's actively evolving to hide inside cells, block our immune signals, or even change its surface markers just to evade detection. And then Step 3, the host system is forced to adapt all over again, deploying entirely new defenses. It's this constant back-and-forth selection pressure over millions of years that has literally shaped the mind-blowing complexity of our immune systems today.
So, to kind of summarize the mechanics of this incredible biological dance we're doing, the final clinical outcome of any infection really comes down to a delicate equilibrium between three interacting forces. Force number 1, the microbe's ability to multiply and cause harm. Force number 2, the host's ability to actually defend itself. And force number 3, the tissue damage that is inevitably caused by that very immune response. We really have to completely move away from that old simplistic microbe versus human war metaphor. It's not just a battle. It's a highly complex equation of pathogen multiplied by host multiplied by the immune response.
Which brings us to a thought I want to leave you with today. Is our immune system just a shield, or is it actually a record of our evolution? You see, when we study immunology, we aren't just looking at a biological defense mechanism. We are quite literally reading the historical record of how humans and microbes have shaped each other's evolution over millennia. Every single mechanism, every signaling pathway, it's a scar and a victory from a past encounter. So the next time you think about germs, remember, it's not just an invasion, it is a profound, ongoing biological relationship. Thanks so much for joining me on this explainer, and definitely keep questioning the incredible science happening inside you every single second.